and will continue talk, but the topic will be shaped to infinity categories. So and will talk about left-right fibrations, Cartesian, co-Cartesian fibrations, and set up the straightening functor.
Okay, thanks for the introduction, and let me, well, the mic problem has prevented me from, thanks the organizer for having me here, so let me say that here. Yeah, so as a non-chromatic, well, none of my research is actually on chromatic or infinity category. Is a great chance to speak here and talk about things. And I would like to thank Hannah, He Yi, and Guchuan and Folin for when I'm preparing the talk. Thanks for their great help. Okay, so regarding this talk, is on the infinity category topic, and I basically prepared that with under the course I took from Annette Stapleton last semester. And the reference he is following is the lecture notes by Marcus Land. I think now is a book. It's called An Introduction to Infinity Category. But I tried to search, I didn't find an available PDF. So if you are really interested, because I think it's a very handy book to read, you can email me and I can send to you. I think that's probably illegal. I don't know. Okay. Anyway, so that's one of the main reference I'm using, and the other ones are, well, Caradon, Homotopy theory. Yeah, like that. So I read through the Charles notes on quasi-category, and I see some like maybe notation will be shifted. But yesterday, David already kind of mentioned all the materials I'm going to talk about, so I'm very happy. And so I think even though the notation might not be consistent, but it will not impact me to tell a story about that. All right, so that's enough talking, and let's get started with with the left and the right vibration. So let's do a recall from He Yi's talk. That the left horn, it is the horn and J where you have 0 less or equal to J less than N. And because you have the very left one, so it's called left horn. And well, correspondingly, right horn means you have the N part, but not the 0 part. Okay, so we can define the left vibration and right vibration using by the lifting property. And I think the two paths, either left or right, are like identical through the op functor. So I'm just gonna choose one. I'll choose left. So we say a map of simplicial set maps to y is left vibration. If it satisfies the right lifting property. If you're like a little bit dizzy about right or left or whatever, then I'll draw a diagram later, so hopefully it'll be clear at that point. With respect to the left horn inclusion. So that is saying if we put left for inclusion on the left, and then put our fibrations on the right, so the fibration will always be on the right. Then we get a lifting of the diagonal. So let me make a note here because it's leftward. Yeah, so if you have this lifting property, then we say this fibration, this map is a left fibration. And if you replace the left for inclusion with right for inclusion, you get right fibration. Okay, so we will first give the definition of co-cartesian fibration, and then we'll come back and talk about the connections and the motivations. Okay, and okay, again, I'm being lazy and have students pre-written. So let's recall the adjunction also from He's talk yesterday. The join and slice adjunction, I don't know if that's the correct name, but okay, so you have start with an S set, and you have two adjunction. It's not symmetric. The join construction is not symmetric. Is there a question? Yeah. So the left join is the left adjoint to this. Sorry, is there a question? Okay, so the left join is, I don't even know if this is called left join. Anyway, this one is corresponding to the slice functor to the over slice, where you send this map to XP over, and then the other one you swap X to the right, and you swap S to the right is corresponding to the slice functor where you send that to P under. And okay, so let me also recall, so this is the simplicial set given by you send the nth level to the slice category S over. I see that in the chat. Let me just briefly check. Yes, I think that's the book. But I don't know if the lecture notes Nat get directly from him is different than the book or not, or how different, but I would guess it's almost the same. Anyway, let's come back. So from those two adjunction, we can get a lemma. So let's pick a diagram of a triple map together in simplicial set. Then we get an induced map in the slice categories. What's in the middle is not X, it's a cross. Sorry about my handwriting. Okay, so there's an induced map through the adjunction. You just need to draw a diagram and play with it. And there is a bijection of lifting problems. So on one side, you have the lifting problem of this. And on the other side, you have a lifting problem of the joint. That's not A. That's A. Okay. To X and Y. Yeah, so the proof of this thing is just play with squares, and I think is a little bit tangent to the topic, so I'm not gonna prove it. You're welcome to do it yourself, or you can look at the book. Okay, so we're gonna use this lemma to see that the two definitions I'm going to give for P co-cartesian morphisms are the same. Well, okay, so I already reviewed that. I'm gonna give two definitions for P co-cartesian morphisms. So the first one is what's in Marcus Land's book. And I think that is easier to understand and easier to see the connection. So a morphism, that is a map from delta 1 to X, is called P co-cartesian if for n greater than or equal to 2, any lifting problem admits a solution. So let me draw the diagram. And this is F. Okay, so here you need to like this part is already in the data, so you need to fix map P to talk about P co-cartesian morphism. All right, and the second definition is what's in higher topos theory, and it is using the description of join. The slice. It also showed up in yesterday David's talk. So it says, let that be an inner fibration and I think here I have, there's a typo in my notes. Okay, it's in X. So then F is P co-cartesian if and only if the functor when I prepared that, I realized it's very easy to swap co or not co. So if I made a typo somewhere, please let me know. Yeah, so this is a trivial fibration. All right, so let's spend some time to see those two definitions are identical. Okay, so because it's a trivial fibration, we know it has the right lifting property with respect to the boundary. So let me draw the square. So the left-hand side, you put the boundary, and the right-hand side, you put this slice, map of slice categories. PX. So this has a solution. And then, okay, so I'm just gonna draw the diagram of what's in the lemma before. And then we can see it. So, okay, if you treat, let me use a different color, the boundary as S and the full n simplex as T, and then this is a I, B, phi, X. Sorry about abusing the notation of F, but if you look at this lemma, which I don't have a copy downstairs, but the sense is we can transfer from the slice this map to the join notion. So just believe me, I checked several times that this square corresponding to this square, which I'm gonna draw right now. Yeah, so those two lifting problems are the same. And let's talk more about the left-hand side map. So this map, is, okay, let me get rid of this ugly arrow. This map is isomorphic to the Horn inclusion from the 0 n plus 2 zeroth Horn. I have no idea how to say Horn, by the way, to the n plus 2 simplex. And it is the inclusion from like delta 1 as an edge to this Horn. It's like the first branch of the Horn. Well, I shouldn't say it's the first branch, but it's like the first stick, if you know what I'm saying, because I can't draw that higher Horn. All right, And I should also say the restriction to delta 1 is given by F. So let's go back and compare this one with the previous definition. You see, well, they are the same. Screen is too small. Okay, and we can almost see them at the same time. All right, okay. So now we have the notion of P co-cartesian. So we can define the co-cartesian fibration. So I think we need to start with inner fibration for this one, but I'm just gonna put that as an actual condition. So a map of simplicial set is a co-cartesian fibration if first it is an inner fibration. And then second, every lifting problem where you put 0 there, and for Cartesian, the right one, you put 1 there. This this admits a P co-cartesian lift. So that means you not only have this arrow, but also that arrow is a P co-cartesian morphism that we define here. And okay, so let's see why. So there is a fact. Left fibration is co-cartesian fibration. Why? Okay, so let's briefly scroll back and look at the definition of left fibration, which is not far from here. So you see all of these, it has a lift of left horn inclusion. And here, let's shrink that a little bit so we can, well, that's too far. Okay, anyway. So from the definition of P co-cartesian, we can see if x and x to y, this is a left fibration, then all the edge you pick is P co-cartesian. So of course, this lifting you're able to find. Okay, I'll stop for questions. Are we all good? All right, cool. All right, so enough definition, and let's talk about why we care about those. And I know that Luri has this like hexagon picture in higher topos theory that I feel like is very beautiful. It is like, I'm not gonna draw it, but I'm gonna briefly talk about it. Like trivial fibration on top is the most strict one. And then here you have can fibration. And from here you have two ways to go. Either you go left or you go right. If you go left, you come through co-cartesian. If you go right, you come through Cartesian. And then you end up the same point as inner fibration. Anyway, that's kind of going from strict to coarse. And why? Still why? Well, I think maybe the motivation is from covering space, but I don't know that for sure. But let's talk about fiber over a point, that is categories fiber over something. And that is the Gaussian construction. So let's assume. So now things are between infinity categories. So I'm swapping notation. Let me write the categories this way. Okay, so we can think about the pre-image of a point under the map P, and for that I mean the square. Let's pick a point and map it in C. Let's say map to X in C, and then we can pull it back along this P. So we get this square, and let's write the slice as epsilon X. So if our epsilon X is nice, well, sorry, I didn't mean to say that. If our P is nice, we can expect the piece here, epsilon X, is also nice. For instance, it is an infinity category. And that nice condition, we can replace that, is inner fibration. So yeah, that's one theorem in Lurie. I don't know the number, but if you have an inner fibration here, and you want to look at the pre-image over a point, and that will be an infinity category. Well, maybe infinity category is not nice enough. What if we want it to be an infinity groupoid? Sorry, before that, let's, no, that's okay, okay. So we have another fact. If P is left or right fibration, I'll choose left. Then epsilon X is an infinity groupoid. It is also, well, infinity groupoid is kind of complex. I'll make it aside. Even though the proof is not easy. I think Nat have that course just want to prove this. All right. So this may give you some motivation why we cared about left and right fibration, because, well, we have the fiber over a point to be infinity groupoid, and they are nice. They are probably the nicest thing you can expect in infinity category. Well, but why do we care about co-cartesian and Cartesian fibration? Well, so let's discuss further about this connection. So actually, this assignment will give a functor from our C to cat infinity. So let's now assume our P is at least an inner fibration, so that epsilon X is an infinity category. So for every X in C, we'll obtain an infinity category epsilon X. So we get this assignment gives a functor from C to cat infinity. And then, okay, so if that's left fibration, you can change the target. You can change the target to infinity groupoid. And that is to say, well, this construction gives a connection between whatever fibrations goes in the construction. With the functors from C to, well, how well your target would be. Well, that's great. Well, so I still haven't said why we cared about co-cartesian. So, well, we so far we have only been looking at fibers over a point, which is, well, part of delta zero. But what about fiber over an edge? So can we say some more about that?
Is it okay if I stop you and ask you a bunch of questions about the fact you just said? Okay, so the first thing is that, like, what you wrote in aside, are those equivalents of infinity categories, like the infinity groupoids and complexes?
Right. Yes. That's an
actually
equivalent
equivalent
as
infinity
infinity
categories.
category. Yes.
Okay,
It's not
great.
easy.
So and then the second question, I get it. Yeah, the second question is that so you mentioned in the fact that if P is a left fibration, the fiber is an infinity groupoid. So is there any restriction? Well, is there any qualifiers you can put on the functor you wrote in the next line that would say this functor actor factors through infinity groupoid? Like you said, like this assignment, like the pullback diagram gives you a functor from C to the category of infinity categories, right? So is there anything you can say about the functor that corresponds to the fact that would say this functor factors through the infinity category of infinity groupoids?
I think what you mean, if I rephrase it correctly, is you're asking how tight this condition is. I think is an if and only if condition, like because you're constructing using this fiber, right? I think only if and only if it's a left or right vibration. I think. Okay.
Okay. So P and really here left and right doesn't matter. Okay. Right, okay. Right. Thanks.
Sure. Other questions?
How can I say the fact is true? Sorry. How can I say the fact is true? I mean, you say if P is a left fibration, then EX is an infinity groupoid.
Yeah, that is.
What if P is a right fibration?
It's also infinity groupoid because for the off functor you just flip the arrow.
Okay. Okay, thanks.
Yeah. So yeah, I left that for you to read, or you can ask me after the talk. Okay, so let's come back to that. So here we are looking at fibers over a point. So what about fibers? Well, I'll end this sentence and say, okay, fiber over like delta 1, an edge. So that means we are asking this square. And I still have my fibration here. And now I'm replacing the point with an edge. And what can we say here? Okay. So that's why we need the co-cartesian condition or Cartesian. I'll just go with the left branch. So if our fibration is a co-cartesian fibration, then okay, how do I put it accurate? Then let's say for every morphism x to y in C, we obtain a functor between their fibers. And if you're doing with Cartesian, you probably have like a contravariant one or something issue you need to worry about. Anyway, and this condition is tight, means it's an if and only if. So that means if your fibration is not co-Cartesian, then you can't get a functor between the fibers. Okay, so yes, I see some remarks in the chat. Thank you. Okay, so we are going to prove this later in the straightening and unstraightening equivalence process. But I would like to say something more about how we are gonna prove that. Well, the problem of not being a functor is, well, you just need to worry about two things. One is a preserved identity, and the other is a preserved composition. And the issue is, well, if you don't have a co-Cartesian fibration, the composition is like, if you pull it back, it will be like two arrows and it's not composable. So that's a problem. And you want to guarantee it is composable. And we're going to solve that in the later context. Okay, so now let's talk about this Lurie's straightening and unstraightening equivalence that, to be honest, I'm still a little bit nervous talking about this because, yeah, I'm not fully convinced I understand the Infinity-Categorical language. Anyway, but this theorem is very fun. It's, well, it's like explicitly using the Grothendieck deconstruction and build a bridge. And yes, what to expect in this equivalence? Let's give some definition first. So this category, the slice category over C, is already show up in yesterday's Davis talk. And well, we basically look at the subcategories of that. And we can look at the subcategory of co-Cartesian fibrations over C, where the objects are the co-Cartesian fibrations and the morphisms are morphisms of co-Cartesian fibrations, namely it's this triangle. So you do want the target to be the same, and you want the co-Cartesian, the morphism of co-Cartesian fibration to send your P co-Cartesian morphisms here to P prime co-Cartesian morphisms in X prime. And then, okay, so that's one subcategory of cat infinity over C. And another one inside that will be left fibrations. We already seen left fibrations is co-Cartesian fibrations, so it's getting smaller and smaller. And actually, that's also a full subcategory in the largest one. And then I'm going to introduce this one that I don't remember if it showed up before. So that's like the infinity category of spaces. It's defined as the simplicial categories of CW complex, and the mapping simplicial set will be you get the mapping space and send it to simplicial sets using the same functor, and you take the coherent nerve, so that's an infinity category, and we call that the infinity category of spaces. Often just think of that as space. It's not that important. Okay, so let me state the theorem. So there exists an equivalence of infinity category. So one side you have fibration. The other side you have functors from C to cat infinity. And then this restrict to one side you have left fibration, and the other side you have to space. I don't think I'm allowed to put inclusion on the right side, but you know what I mean. And actually for the special case, for X is an infinity groupoid, it restricts to the space over X is the same as functor from X to space. So it's the other side of the restriction.
I'm sorry, can I ask another question?
Yeah, go ahead.
Yeah, so what you define as the infinity category of spaces, how is that different from infinity category of infinity groupoids? Because my understanding is the infinity groupoids. Okay.
They're the same.
Okay.
Yeah.
Yeah.
I think I just like copy things from different reference and yeah, not careful about making them.
Okay. Okay.
Yeah, sorry about that.
Okay, great. Because I was sorry, there's something the simplicial category model has to be explicitly set here to make it make sense. Okay, great. Thanks.
Thank you. All right, so that's the statement of the theorem, and let's talk about the ideas. Well, the proof is four pages long. I'm not gonna go through the proof for sure, but let's at least construct the very basic case, and that's also kind of giving you a proof of why it is giving a functor between the fibers. So the idea is construct a functor okay. So let's start with informal construction. So let's start with a co-cartesian fibration. So then we have, well, for each X in C, we have an infinity category epsilon X, and for each edge in C and an object Z in the fiber, we can choose a p co-cartesian lift. That we call z to w of f. Maybe it will make more sense once I draw a diagram. So we denote this w as f lower shriek z. Okay, so what is going on here? So here you have the edge f, and then for every z chosen here, you can find a w, and this is f lower streak. And this edge is p co-cartesian. Okay, does this make more sense now? All right, and this all comes from the properties of Cartesian fibration. And we also have for another z prime, also in the fiber, and an edge between z and z prime. We can choose another p co-cartesian lift. From z prime to w prime, that is also f lower shriek g prime. And with the square commute, okay. And the choice of f lower shriek alpha is contractible because all the map is p co-cartesian. You can go back and look at the definition, and it is pretty straightforward. I don't know how to spell choice. Okay. So you may already guessed, okay, that this is solving the problem, because remember what problem we have for it not being a functor is like when we pull it back, we have two arrows and it's not composable. Well, but then I know that the difference between this like source and target, if there is a difference, then the choice of that thing is contractible. So we can actually compose it. And this is actually building up to the definition of Cartesian fibration. So it is really the tight condition. And from here, you will see, okay, I know why the definition of co-Cartesian fibration is like that. So as a conclusion for edge, it gives a functor. The f lower shriek between the fibers. Okay, so I think I can expand this, but maybe not based on the time constraint. I think I have things left to show. Let me briefly talk about that. I have to show that the association from F to F lower street is functorial, and that requires some like two-dimensional work. But yeah, I think I have that. I have more written in my notes, and you can come back and look at that. But for now, yeah, I will move on to the special case that David mentioned yesterday. Okay, so let's consider the case that our C is cat infinity. So let me go back to the theorem. So if our C is cat infinity and we only choose the identity functor here on the right side, we'll get something on the left side that is a co-cartesian fibration, and that is called the universal co-cartesian fibration. In the sense that every co-cartesian fibration is a pullback of it. So the notation is point slash slash to cat infinity. Okay, so, and am I allowed to provide, yeah, let me give a slightly more detailed description of this category. So this has object as pair C and X, where X is in C, and the morphisms from one pair to the other pair. F and alpha, where your F is from C to D, and your alpha is a morphism from Fx to Y in D. So you see that's actually the Gaussian deconstruction over point. So, all right, so I have one thing to talk about, and honestly, I know nothing before preparing this talk, that is stack. And half algebroids, but they are fun. So let's briefly talk about that. The connection is also mentioned yesterday. I'm very glad David mentioned that. Because that's an example of things fibered over groupoid, but I think here most of the resource in algebraic geometry you look at is fibered over like strict one groupoid, but not infinity groupoid. And then that is causing some issue because, well, let me talk about the example first. So a stack is a sheaf of groupoids, and it satisfies the effective distance that's like the Green condition of vector bundles. So we can build it through the example as say for any space X, and we grab an open set, open space inside X, and we can assign it with a groupoid. The objects are here. Here are the real M-plane bundles, and then the morphisms are bundle isomorphisms. And then you sum up all the open sets here in X, and then this collection is a sheaf of groupoids. And you also want it to agree on the intersection of open sets. So it's exactly like the vector bundle condition, and you have the cocycles like that. But it has an issue that the assignment from U to wrong color, from U to this sheaf of groupoids, this is not a functor. But if you move the context to infinity category and replace the groupoid with infinity groupoids, you have no issues. Okay, so okay, what more I want to say about stacks? So stacks form a full subcategory of the category of pre-sheaves of infinity groupoid. And there is also a model structure where stacks are the fibrant objects. And then let's put things, let's talk about things and then come back to why I'm talking about these. Okay, so the notion of half algebroid, basically all I deal with is standard algebra, but it's like different than what's happening here. So here is like a pure abstract definition. But let's talk about some geometry before we move to that. So there's another thing called spectrum that is associated to a commutative ring. So the spec R is representable functors on the category of commutative rings. So it's different with the spectrum we just talked about, and it has no connection. Okay. So a half algebroid is actually a groupoid object. And what's in that is a pair. Like all of them is algebras, are algebras, and gamma is a module on A. And it's a left and right module, and they're not the same. The module map is given by the left and right unit. Usually, this is not how I remember things. I remember this thing from this diagram. And this diagram is from Ravenel's Orange Book, Appendix A. I think this one is actually A. Yeah. So you have the co-unit, unit 0, 2, left and right, and you have the co-multiplication. You have the antipode, also called conjugation, such that this diagram commute. You need to be careful that the conjugation is not a module map. So you have this gadget in the middle coming up. Anyway, let's skip the details and see why we cared about that. The thing is, we can get a groupoid from this data such that when we have like a map between rings, between the base ring that is good enough, then we will get an equalizer diagram of groupoids. And it's also giving us a stack if you apply the stackification. So yeah, the example is very degenerate. And I think the motivation why we want to connect that lies in chromatic, because we're going to talk about formal group law and the MU. All right, so let me use the 1 minute to talk about that very important example. Right color. So let's start with the Lazard ring. And by theorem, it is mu star. And we can think about something called W that is almost mu star mu, but it's not quite. So if you replace this B0 to be 1, then it is mu star mu. So of course, it's a module on Lazard ring. So we can build a groupoid and use that to build a stack from there. So. And let's give it a name called MFGL. So the morphisms from spec are to this stack. It's classifying all the equivalence classes of formal group laws over faithfully flag extension of R. And okay, what else I want to say? Oh yeah, I think this stack is called the moduli stack of formal group laws. All right, so I'm 1 minute over, so I'll stop here.